data sets and trying to fit them into linear models. In this video, we'll do it by hand, and then in a second video, we'll do this using our graphing calculators, okay? Now, we often make scatter plots or scatter diagrams to help us see the relationship or correlation that exists between two variables. We're trying to make a comparison between two variables to see if there's any sort of relationship between them, okay? There's a ton of real-world data that can be modeled by a linear function. So the three graphs that you see in the top here, these can show you the different types of correlations you can get in a linear situation, okay? So the first would be your data points follow an upward linear trend, and we would consider this a positive correlation, okay? That means that as the variables for x increase, or the values of x increase, so are the values for y, okay? Here would be a negative correlation. You have a downward trend to the points in your data set. As one variable's value increases, the other's is decreasing, okay? And then here's a situation where it definitely would not be appropriate to model with a linear function. These points are all over the place. There's no linear trend to them, okay? Now, the graphs down here talk about the strength of correlation, okay? Notice these points line up closer to one another as compared to all of these points, okay? So these points would probably have a stronger linear correlation as compared to all of these points. A linear model might be appropriate here, but it's probably going to have a weaker, overall validity to it, okay? And then here, definitely no linear correlation, but you can see there's kind of a quadratic trend to it. So this one would be a little bit more appropriate to model with a quadratic function, okay? All right, moving forward, here I have a data set that's comparing the relative humidity as a percentage with the apparent temperature, okay? So understand the scenario here. Up at the top, we're talking about the actual temperature is 72 degrees Fahrenheit. And then what the data is showing is what the apparent or feels like temperature is based on the humidity outside, okay? So we're very familiar with this in Ohio. We have a lot of humidity, right? So high humidity makes it feel hotter outside than it actually is, okay? So you can see when the actual temperature is 72 degrees, if you have no humidity, it actually feels a lot colder than it actually is. If you have 100% humidity, it makes it feel a lot warmer than it actually is, okay? So I've taken this data and we've made a scatter plot over here, and you can see from this scatter plot there's a definite upward trend, right? It's appearing that as the relative humidity increases, so is my apparent or my feels like temperature. It's increasing as well. So I would say, even though there's not a true linear relationship here, right, the average rate of change is not constant from point to point. That average rate of change is very similar from point to point. So I would say we could represent this data with a linear model, okay? So what I'd like to do is do this by hand in this video, okay? To do it by hand, all we're going to do is choose 2 points from our data set. And you want to pick 2 points that are, relatively well representative of the data set. If there are any points that are outliers in the data set, you don't want to pick those, okay? So you can see I've chosen the points 1065 and 773 to build our function. I find the slope between those 2 points. Turns out to be 2/15, or that's approximately 0.13 repeating, okay? I want to interpret what that slope means in the context of this situation, okay? And here's where I think the decimal approximation is very helpful. I'm thinking of the decimal approximation as 0.13 repeating over 1. Okay. Now we know slope is a measure of the change in the y values to the change in the x values. In this particular data set, your y values, well, what do they represent? They represent your apparent temperature. And what do your x values represent? They represent a percent increase. Okay? So basically what we're saying here is that this slope means that for every 1% you increase your relative humidity, you can expect a 0.13 degree increase in your apparent temperature. Okay? That's what that means. All right? Now, moving forward, once we have our slope, we're just going to take that slope and we're going to pick one of these 2 points to build our actual equation to represent the data set. I've chosen the point 1065, and I think it's actually better when you're building the equation to keep the fraction of the slope to where everything is still exact. So if you come down here, you can see I've got the point slope form using 1065 and the fraction version of that equation. And then I've put it into slope intercept form. I kept it exact here, but then I also approximated as well. Okay. Now, once we have the equation to model the data, we can use that equation to predict other values that aren't directly within the data set, values that didn't show up in the table. Okay. Now, there's 2 types of predictions that you can do. You can interpolate or you can extrapolate. All right. Interpolating means you're predicting a value that is inside the domain and the range of the data set. Okay, so if we went back and we looked at our table here, our domain stretches from 0 to 100%. Okay, and then the range is anything from 64 to 76. So as long as we're trying to predict values within those intervals, then we would be interpolating. Okay. Now, extrapolation is predicting a value that's outside the domain and the range of the data set. So if we were trying to come up with any number that's not between 0 and 100%, which doesn't really apply here, that would be considered extrapolation. Okay. All right, so what can we expect the apparent temperature to be if the relative humidity outside is 35%? Okay, and is this an example of interpolation or extrapolation? Well, 35% definitely falls within the interval of values in my table, right? Again, my table stretch from 0% to 100%. 35's, in between 0 and 100. So this is an example of interpolation, okay? What I'm doing is I'm just taking the 35%, I'm plugging it in for my x value in my equation, and then simplifying for y. Turns out to be 68 1/3 degrees, or just over 68 degrees is what I can expect it to feel like when I have 35% relative humidity. Okay? All right, that's it for this video.